Uh, Good morning, everyone. My name is Tomiwa Aderemi. I'm a PhD student at Heriot University, and I'll be presenting a part of my research today. So we all agree that mine workings have uncertainties that are unique to their location and their mining history. But the key question is, how do these uncertainties impact hydrothermal performance metrics? And more importantly, how can we learn to adapt operational control strategy under uncertainty? To do this, we need to first of all identify these uncertainties and then characterize them so that we can develop a framework to predict target objectives that are relevant to heat recovery. And examples of target objectives can be production lifetime, useful energy, and power. So the image here just visualizes this concept using data from the Glasgow UK Geos as a case study. And the map view on the left here just shows a conceptual mine working geometry in a sector model within that Glasgow UK Geos area. And we can see the corresponding line of section on the right, which is the line of section along AB. And today, I'll just be trying to talk about how we can pick out the uncertainties in this kind of framework. So the image on the left here just shows an example of a map view within the geological zone of the Glasgow main mine working. And we can see that in this example, there's spatially varying lithology around two conceptual mine workings, room and pillar mine workings, right? So in this image in the middle, so I've digitized a real mine working, but I've also assumed a laterally extensive coal seam in this sector model. Today, I'll be focusing more on a simpler case study, which is a conceptual mine working geometry with backfill material in the, modeled in pink here. And then I have a producer, which is abstracting mine water at ambient temperature and re-injecting the thermally spent cold water back into the mine in an open loop configuration. And all the simulations that I've carried out today, I've carried out using an open source numerical simulator developed at TU Delft called OpenDart. So my uncertainty workflow actually decomposes the uniqueness of uncertainties in mine water geothermal systems into three broad categories, and they are hierarchical. And these categories actually span different subject matter domains. And as a modeler, some of the things that come to mind is, how am I able to discretize the mine workings, the geometries of the pillars, the galleries in one grid cell, the complexity, the connectivity, because I don't want to lose some of the information in that mine. So how am I able to discretize it in space and in time? In time will be much more relevant when you're looking at cyclic loading, because you don't want to miss some certain things. Another question that comes to mind again is, how am I initializing temperature in the model? Am I using a simple gradient-based initialization method, or I have different temperature logs and I'm able to create a full 3D temperature model? Because these things actually affect the way your thermal plume propagates. And remember, previously I said the aim is to actually predict, not react. In my model, I've been able to represent the heat capacity and the thermal conductivity. I've constrained it to the lithofasces, the distribution of the lithofasces within the system. And I can keep going on and on to mention different kind of uncertainties. But today, I'll just focus on backfill sensitivity, the impact of backfill volume sensitivity on the thermal hydraulic accumulation in a particular mine. And I'll also talk about the impact of confining layer properties. So basically, I'll be using continuous simulations with a single doublet to do this. So here are 3 different metrics that are commonly used to quantify performance in geothermal systems. There are more performance metrics, but one of the advantages of using a full field numerical simulation is the fact that we can have pressure constrained thermal storage capacity and recovery. What do I mean by that? So in this analogy in the curve above, what that means is that if you have a producer, the useful production above your cutoff temperature must be constrained by the drawdown in that borehole. And I mean, some of my colleague in the last presentation and the previous presentations have also highlighted that. But again, even though the simulation runs below, the cutoff temperature, and in some cases, it might even go outside the contract period, everything below the cutoff temperature will be termed as uneconomic to the project life cycle. And that actually forms a basis for us to be able to constrain our thermal production time. So the way I've defined the host rock heterogeneity scenarios, I've defined them based on the differences in the interpretation between the density and the sonic derived logs, which I was able to get from the exploration borehole within that area. And I was able to get 2 different distributions, a low case porosity permeability scenario 1 in teal, and a high case porosity permeability scenario 2 in purple. And I've also calibrated this to some experimental data, which has been published also. So let me stop on the static model side of things, and I'll share with you some dynamic simulation results from OpenDARTS. So the image here just shows temperature evolution curves in the high host rock porosity permeability scenario 2. And I've also increased the backfill volume from as you move. So we have progressive increase in backfill volume as you move from 0 to 1 to 3 to 6. And what you can see here in the plot on the right is that you have a decrease in the temperature recovery as you increase the backfill material volume within the mine. And same thing you get when you look at the low porosity permeability case. So basically 2 things are going on. We are varying the host rock heterogeneity, and then you are also progressively increasing the backfill volume. And this is quite intuitive, right? But when I introduce a backfill material, if you look at the map on the bottom left, when I introduce a backfill material in between the flow pathway of the injector and the producer, we can now see the impact in the dashed lines. So the high host rock permeability scenario 2 is the dashed line here, and then the teal line is the low porosity permeability scenario. And we can see that there is delayed breakthrough time in this case. Now, note that there is a disconnect between the producer and the injector. And the impact is felt more in the high host rock permeability scenario, right? But that picture won't be complete until we show the pressure evolution, right? So when we look at the pressure evolution, we can basically divide this curve into the transient phase, which is the early time, your mid-time region, and then your late time region, which is more or less like your steady state. And what we can see immediately is that all the previous cases, they are all bunched up just very close to the hydrostatic pressure, which is what we expect in an open mine with very large storage capacity. But as you decrease the porosity and permeability in the confining layers, you get an increase in the differential pressure between the injector and the producer. And you can see that effect in these 2 curves here. And this is very instructive. Whatever goes on in the early time region, in the transient region, is actually very instructive, to understand the way our system behaves. And this plume is just a different way to visualize the data, right? In the high host rock permeability below, we can see that the backfill material in between the producer and the injector has changed the thermal sweep pattern. So it has more or less like created preferential pathways for the temperature to evolve. And what we see in the lower image here, the scenario 2 high host rock, is that you have a mixture of advective heat transport and conductive recharge, right? And you have delayed thermal breakthrough at the producer here, compared to the low host rock scenario, right? So this kind of gives us an idea of how the thermal plume is propagating, and this is all predictive. So a different way to look at the results is, comparing different ensembles of sensitivities and benchmarking it against different performance metrics. And the scenario 2 is in purple, the scenario 1 is in green. But what we can see immediately is that for the scenario 2 host rock heterogeneity cases, it looks as if it's better when you're looking at the useful energy that has been produced. It looks as if it is better, but what this also shows is that because you have a longer rectangle in the interquartile range of the box plot, it makes the system more sensitive to how you actually operate it. So if we focus on this operational control here, we see that there is higher sensitivity, basically, compared to the scenario S1. And also, this is looking at power, basically, right? You can compare the two power scenarios. So what you see is that the power is actually governed by the mine working hydraulics, not the host rock. The host rock actually determines how you are able to sustainably produce that heat delivery rate, that power. And this slide, in conclusion, is a different way to actually look at an ensemble of results. So what I've plotted here is power on the y-axis and then production lifetime on the x-axis. The size of the bubbles are the cumulative water volume produced over a period of 12 years. So just to wrap up very quickly, we can see that there is an ensemble of results that creates a kind of reference condition for a reference design. And by the time you begin to modify the operational control, you can get higher performance, which is this cluster above here. And so in conclusion, the operational control sort of acts as a modifier, and it dictates how the geological and geotechnical uncertainties manifest, especially when you're looking at different target metrics over time. And a full field simulation actually helps us to leverage the data available within a particular mine concession so that we can have a de-risked evaluation of thermal recovery. So thank you very much. And yeah, thank you.